Hello. We are very happy to welcome a truly revolutionary figure in not only African American history, but American history overall, Herman Brenner White. Hello, Dr. White.
Hi, how are you?
I'm doing well. My first question is, when did you first realize you were interested in nuclear and particle physics, and what about those fields truly caught your eye?
Well, I guess I should say that I was always interested in science and had a good chance to operate in the community I grew up in terms of looking at the science and looking at the kind of things that the colleges and university atmosphere afforded me. Now, when I decided to go to college, I was interested in nuclear accelerators, or nuclear reactors, actually, and doing work in that particular area because that was more of an engineering motivation than anything else. However, after studying in college for a while, I saw that the breadth of questions that you could ask about the origins of the universe and the size of various things and the work that we were able to do became very, very important in terms of understanding the entire universe as it is. And so that required studying physics, and studying physics at a level that was a little bit more than preparation for engineering. And so I started to do that kind of work and to study at that level, and I really enjoyed that. But I also felt that there were a lot of other things that I really wanted to accomplish, and in doing so I started to essentially focus on particle physics because that was sort of the ultimate questions that could be asked about the origins of the universe and the size of things and how much was actually in the atomic structure that everyone else was studying.
Very interesting.
Okay. Can you tell us about one or two significant challenges that you faced while you were becoming a physicist and how you overcame them?
Well, I guess when you say in terms of challenges, one of the things that I did as a young scientist was to go to a laboratory that was being operated and developed to do research at an energy that had never been seen on this planet before. Now, that in itself was a challenge, not just for me, but a challenge for anybody who's doing the science there. It turns out that everyone basically was motivated to try to understand all of the laws of nature and how the laws of nature operate. So for me, I thought that doing that particular work was somewhat noble, if you want to know the truth. Now, as for challenges, getting prepared to be able to pursue that kind of work was very, very, very difficult because there are only a few places that actually will teach you how to essentially develop the skills in computing, develop the skills in mathematics, to develop the skills in certain types of physics studies to be able to pursue that kind of work. And I did not have access necessarily to all those institutions or all the people who were engaged in it. In fact, there's a select group of people now who are engaged in doing elementary particle physics because it is so difficult and the machines are so large and the detectors are so large that you have to go to where the research is being done rather than have the research done wherever you happen to be. So for me, given my background and given the amount of additional work that I had to do to get to the point of understanding how to pursue that research was really quite a challenge. But you have to stay up nights, you have to work weekends, you have to get as much help from everybody that you can to be able to, if I may use the term, catch up, to be competitive in a field that basically people are studying things for the very first time. And I overcame that basically by just hard work.
Very admirable. You spoke about this already at the big session, but just for the interview's sake, what societal impacts have you seen firsthand by gains made through the civil rights movement in your field?
In my field, there have been some civil rights impact. And I say that only because of the fact that access to the kind of training that I have had is now more open and capable with regard to many students. So for example, when I was in an undergraduate education, I did not have another African American student in any class that I took. I did not have an African American professor. Not that necessarily one has to have that sort of thing, but if you're talking about society, if you're talking about segregation or if you're talking about equal opportunity, then you would expect then to have a larger number of people who are engaged in the same sort of things that you're engaged in. So I felt very much like this is a unique situation in the fact that now when I go to classes or I go to a great institution like IMSA, I see a significant number of people who have been, how would you say, in the minority population who are engaged in doing science and looking at science and being trained in science. And that's a new thing, and I think a very healthy thing for our country and for the world for that matter.
I know you stated that you worked at Fermilab, so is there anything in physics that has changed over the years since you started working there to say now?
You mean in terms of the science or in terms of the laboratory itself? Fermi National Accelerator Laboratory is a Department of Energy Office of Science high energy physics lab. For many years, from the time that I joined that laboratory until 2 years ago, it was the highest energy particle accelerator facility in the world, which means the world came to our laboratory to do their research. I would say that the Fermilab has certainly changed over the years because, as I said before, what we did was pioneering work. You could not do this kind of research anyplace else. So everything that was done there, every experiment that was performed there, whether they were successful or considered to be successful, or whether they had an outcome that you didn't expect, was always something new. And so when we do experiments in that kind of environment, we expect new things. We expect discoveries. We expect to verify ideas that have been put forth but not able to verify them because the energies of the interactions that you're studying had not been accessible. So yeah, I think it's clear that many things certainly changed at Fermilab over those years. And I've been there for 39 years. So I've seen lots of changes in terms of the different types of experiments. When I first started at the laboratory, my first experiment took 10.5 months. So from the time we started doing the research to the time we published the paper was within 3/4 of a year. My last experiment, or one of my last experiments, took 10.5 years. And so the difference between the complexity of the experiments that you're doing has certainly increased a tremendous amount. Some of the detectors that we had weighed maybe about 100 pounds or 200 pounds in the early days of the 1970s, some of them, depending upon the experiment. The last detectors in our colliding programs were 5,000 tons in weight. And so you can see something from a few hundred pounds or maybe a ton or two to 5,000 tons to do the same or similar type of research. And that's something that has changed tremendously there.
I was actually on the History Makers website about 2 or 3 days ago, and there was a small portion about you wanted kids to acknowledge scientists the same as they acknowledge like athletes and comic book superheroes and all of those. So my question is, what advice would you give to aspiring scientists, especially those from underrepresented areas?
The advice I would give is that you have a passion for doing science. That's somewhat unique. You should stick with it. You should embrace that passion because it will sustain you. I'm certainly happy to be entertained by sports heroes and that sort of thing, but I do understand, and I think maybe one could say it in a way that the problems that we have on this earth and the problems we have in our country will be solved by changes that are done by reducing our ignorance. What we do in science effectively is to reduce our ignorance. We make assumptions about global climate change, about particles coming from the interior of our sun, about how a particular type of compound will help our arthritis or will help us to survive better or live better. These are all assumptions, but science is the one thing that will make it possible for you to investigate whether it actually is the truth. And in science, reproducible observations are the truth. So when I see young people and I say, you're interested in science, I say, go for it. I mean, really go for it, because these days, we don't have as many people who are interested in doing science. Everyone is interested in seeing science done, but it is a very difficult job and it's very rewarding to do it. You have to commit yourself to it, and I mean really commit yourself. You just heard me talk about one experiment, that my first experiment at Fermilab took 10.5 months. My last one took 10.5 years. Well, now these experiments take 10 years at a time. And if you look at your life's work, sometimes your life work will be 30 years. And so if you think about an experiment that's going to be a third of your entire working life, that does require commitment. So young people who are interested in doing this should understand that, but also understand that that's exceptional, because anything you learn that's new will change everything. Everything that exists in our entire universe gets changed because we can perceive it correctly rather than perceive it incorrectly. And that's what science does for you.
Okay, so you said the experiments usually take, well, not usually, but 10 to 10.5 years nowadays. So is there anything you're working on now?
Well, right now I have two experiments. One is called the muon to electron conversion experiment. And this experiment is designed to look at the properties of a particle called a muon. Now the electron, everybody's familiar with that. The electron you get out of the wall plug, or electrical current. But the muon particle is a type of elementary particle that has many of the same properties of the electron, except it's 200 times heavier. And we want to answer the question, why does nature actually have a particle that looks just like another particle except for this one or two properties that are different? Why are both of these properties and both of these particles necessary in terms of the whole particle zoo? And so our experiment is designed to make an extremely precise measurement of this particular particle property. So we look at a particular particle called a muon, and we see, in fact, if it can change itself into an electron. Because the only difference is the mass, so we think maybe we could capture some of these muons in the body of an atom and then watch that muon convert into an electron and measure the properties of that electron. That would be a tremendous discovery. I won't say discovery because we know muons exist, but it would be a tremendous measurement, and it's something extremely rare and has to be done extremely precisely. The experiment that we're building to do that is called the mu to E conversion experiment. You can find out about it by looking at the Fermilab website. But also the fact is, this is an experiment that has been tried in a number of places, and what we get are limits on how well we can make that measurement. So we're building a much bigger detector, and we're going to make a much more precise measurement of the properties of this muon. Maybe we'll see the muon convert to an electron. You never know. The other experiment has to do with measuring the properties of the kaon particle. I think in my presentation here at IMSA, I made the comment about kaon particles and the fact that kaons decay in a particular way, and it tells us something about symmetry properties that exist in the universe, matter versus antimatter. And what we're trying to do now is to increase our knowledge about the kaon meson particle and see, in fact, if we can make some good measurements with regard to that particle, and do that in such a way that we can understand how rarely it decays into particular type of decay products, in particular the muon and two neutrinos. And that experiment will take an enormous amount of beam and an enormous amount of time to do. It has successfully been done before. There have been 3 events, and those events have been generated over a period of 6 or 7 years. So we're trying to get 100 events. And guess what? We need a lot more beam to be able to do that, and that's why we're doing it at Fermilab.
Okay. Okay, well, those sound like very interesting experiments. Thank you for letting us interview you, and thank you for joining us. We hope that you come back soon, and maybe we could follow up on those experiments.
Thank you so much. I really appreciated being here, and thank you for your question.